Welcome to Mrs. Z's Chemistry. In this video, we will discuss molecular polarity. We learned in 7.2 that when two atoms share electrons unequally, a bond dipole results. The more electronegative atom in the bond has a higher ability to attract the electrons to itself than the lower electronegative atom. So, we have more electrons hanging around the more electronegative atom. Because electrons are negative, a partial negative charge results on more electronegative element, and a partial positive charge results on the less electronegative element. This set of data on hydrogen to halogen bonds shows that as we move down a row on the periodic table, the atoms become successively less electronegative. The larger the dipole moment, the larger the electronegative difference between the two atoms and the more polar the bond. This is the periodic table listing the electronegative numbers for each element. You can see the electronegativity increases as you move to the right on the periodic table in a row towards fluorine, and as you move up in a column towards fluorine. Fluorine is the most electronegative element on the periodic table. Let's determine if the bond is either polar or not by comparing the electronegativity numbers from the previous chart. So if we look at lithium and fluorine, we have a very large difference. We've got lithium over here and we have fluorine over here. We also know that when we have a metal and a nonmetal, then we have an ionic bond. So we don't really even call it polar anymore. It's so polar, it's ionic. When you have two atoms of the same type, fluorine, their electronegativity numbers are the same. So the difference between them is 0. Therefore, we have a nonpolar bond right here. And if you look at hydrogen and fluorine, these numbers are also very far apart in number. Hydrogen to fluorine, we also have a polar bond. Roughly anything that is 0.4 or greater in difference is a polar bond. And once you get up to about 1.7 or 1.8 in difference, that is an ionic bond. Hydrogen to oxygen is a polar bond if you compare their numbers, and carbon and oxygen is also a polar bond. Let's go and look at those really quick. So we have hydrogen and oxygen has 2.1 to 3.5 difference, and then carbon to oxygen also has a polar difference, 2.5 to 3.5. If we want to determine whether or not the whole molecule is polar or not, we have to look at both the bond polarity, as we just have, as well as the shape or geometry of the molecule. If the polar bonds are symmetrical to each other, then the overall molecule is nonpolar, and we say that the polar bonds have canceled each other out. If the polar bonds in the molecule are asymmetric or not symmetrical to each other, then they don't cancel out and the overall molecule is polar. So now let's look at the same set of molecules here, and we're going to determine if the whole molecule is polar or not just the bond. So we're going to start with carbon dioxide, CO2. If we draw this Lewis structure, we have a molecule that looks like this. The carbon-oxygen bond is polar, so we can draw this arrow in the pointing in the electronegative difference. Oxygen is more electronegative than carbon, and we put a little positive sign on the opposite end of the arrow to show the partial positive. And then we have another arrow pointing in the opposite direction towards the other oxygen. So you can see that these bond dipoles cancel each other out. Therefore, this whole molecule is actually nonpolar. The bond between carbon and oxygen is still polar. The electrons are still hanging around the oxygens, but we have equal and opposite poles on either end of the central atom. You can kind of think of a tug-of-war where you have equally strong people on either end of the rope. The rope is not going to move in either direction. It's going nowhere. The strengths are canceling out. Now let's look at water. Let's go ahead and draw water according to its shape. So we have an oxygen and two hydrogens. The shape has more of a tetrahedral shape if you take its electron geometry into account, and if you would take its molecular geometry into account, this is a bent molecule. The lone pairs actually are residing on top, so to speak, of the oxygen atom, and the hydrogens on the bottom. So we have a polar bond between hydrogen and oxygen. Oxygen is more electronegative than hydrogen. So our bond dipoles are pointed in these directions here as I've drawn my arrows. They are the same strength, but they're not pulling in opposite directions. So we have a partial negative side on oxygen and partial positive on hydrogen. Water is a polar molecule because the bond dipoles do not cancel. Now let's go ahead and look at hydrogen and fluorine. Simple little Lewis structure here. We have a bond dipole between hydrogen and fluorine pointing in the fluorine direction, and there's no other dipole to cancel out, so this is also a polar molecule. Between fluorine and fluorine, this is a non-polar bond, and there's only one bond, so this is a non-polar molecule. Of course, we already determined that lithium fluoride here is ionic. It's neither polar or nonpolar necessarily. We call it ionic instead. It's so polar, it's ionic. So now let's look at BF3 here. This one's a little bit interesting. We're going to draw it with a correct shape here. The 3 fluorine atoms are going to spread out away from each other as much as possible and form a trigonal planar shape. So we have a bond dipole between boron and fluorine. It is a very polar bond. If you were to look at the electronegativity differences, it's almost ionic. Sometimes even is considered ionic. But here we're just going to still consider it covalent. So we have 3 bond dipoles that are pulling in equal, and it's hard to imagine that these are opposite trends, but kind of imagine maybe in elementary school you played with this huge parachute-shaped piece of fabric. It's like a thick piece of fabric that is very large, and it's a circle, and there's these little handles all along the outside edges. So if you could imagine 3 different people pulling, they're evenly spaced around that circle, and they're all equally strong, and they're pulling all very, very at the same strength, then the parachute's not going anywhere. So it's kind of like a similar tug-of-war idea here. This, all the bond angles, cancel out, and we have a non-polar bond between BF3 here, or it's a non-polar molecule, even though we have very polar bonds. All right, so I know that figuring out if the bonds cancel each other out can be a tedious way to determine if the molecule is polar or not. So here's a much simpler way. Let's look at it this way. Ultimately, we need to determine if the molecule is symmetrical or not. If it's symmetrical, then the electrons are shared evenly or equally around the molecule, and it is nonpolar. If the molecule is asymmetric or not symmetrical, that means the electrons in the molecule are not shared equally, and it is a polar molecule. When we determine molecular symmetry, we are not going to try to cut the molecule in half like we do in math to determine if a shape is symmetrical. This doesn't work out very well for molecules. Instead, we are going to look at everything around the central atom. If all the electron domains are identical around that central atom, then that means the electrons in the molecule are shared evenly or equally between all the atoms, and the molecule is symmetrical and nonpolar. So let's look at everything around the central atom of this NH3 molecule. So nitrogen is our central molecule, or atom. Remember that an electron domain is either a single bond, a double bond, or a triple bond. Each of those count as one electron domain, or a lone pair of electrons. A lone pair of electrons are these 2 dots on nitrogen. That is what we call a lone pair. They are alone because they're not being shared with another atom. They just belong to nitrogen, but they are a pair of electrons. So we have 1, 2, 3, 4 electron domains around nitrogen. All 4 of these things are not identical. We have 3 hydrogen, single bonded hydrogens, and 1 lone pair. Therefore, NH3 is not symmetrical, and it is a polar molecule. Now let's look at this HCN molecule. We have carbon as our central atom. We have 2 electron domains around carbon. A triple bond counts as 1 electron domain. A single bond counts as 1 electron domain. We don't look at the lone pair on nitrogen. We only care about what is around the central atom, in this case, carbon. There are 2 electron domains around carbon, and they are not identical. Triple bonded nitrogen is not the same as a single bonded hydrogen. Therefore, this is a polar molecule. Now let's look at this PCl5. We have phosphorus as the central atom. We have 1, 2, 3, 4, 5 electron domains around phosphorus. They're all 5 identical. This is a non-polar molecule. the electrons are evenly spread out throughout the whole molecule. Now let's look at this N2 or nitrogen molecule here. It might be a little bit tricky to determine this because there is no central atom, but you can imagine that two nitrogen atoms are going to equally and evenly share electrons around them, and so we have a nonpolar molecule here.